Welcome to this deep dive. Today, we are looking directly at you.
Yeah, specifically our listeners who are, machine learning practitioners, quantitative data scientists, applied mathematicians.
Exactly. Because our mission for this deep dive is to systematically unpack a pretty groundbreaking 2025 paper by Qinmeng, Luan, and James Hamp. It's titled Automated Regime Classification in Multidimensional Time Series Data Using Sliced Wasserstein KMeansClustering. Clustering.
It's quite a mouthful, but honestly, if you build market models or work with complex, noisy time series, this research proposes a fundamental paradigm shift.
It really does. I mean, usually when you're modeling financial markets, there is this expectation of precision that we've kind of borrowed from traditional engineering.
Right.
You look at a time series, you fit a parametric model, and then you hunt for structural breaks.
Yeah, the traditional econometric approach basically assumes a clean, discrete fracture in the underlying math. Methods like the classic Bai and Perron global breakpoint search, they rely on defining a system through static equations. So when the coefficients of those equations abruptly shift, the analyst flags that exact moment as a regime change.
Right, like going from a bull market to a bear market.
Exactly. Or, low volatility to high volatility.
Okay, let's unpack this. Because anyone who has traded or modeled high-frequency financial data knows that the clean structural break approach, it rarely survives contact with reality.
Oh, almost never.
Especially when you expand beyond a single dimension. When you're looking at portfolios, global asset classes, pairs trades, the data just doesn't conform to neat parametric assumptions. It is messy.
Highly messy. And that's exactly what Luan Hamp's paper attempts to solve. They want to map these multidimensional market crashes without relying on a single parametric model.
Right, so rather than fitting a mathematical jacket onto the data to see where the seams rip, we are analyzing the changing geometric topology of the raw data itself.
Precisely. They are completely abandoning that mathematical jacket. Instead, they treat multidimensional time series as evolving probability distributions.
Which is wild.
It is. They use unsupervised learning, specifically optimal transport theory, to cluster those distributions based purely on their geometric shape.
But to even begin applying a clustering algorithm, you have to translate a continuous stream of price ticks into a format the algorithm actually understands.
Right, the data preparation phase.
Yeah, the authors call this the lifting transformation. So let's break down the mechanics of what they're actually doing to the raw data before any clustering even happens. Sure.
Yeah.
So consider a continuous multidimensional data stream. In a financial context, this is your discretely observed price path for multiple assets over time.
Okay.
The very first preliminary step is converting that raw price path into standardized log returns.
Which makes sense because that normalizes the scale across different assets, so a wildly high-priced asset doesn't mathematically overpower a low-priced one.
Exactly. Standardizing gives us a mean of 0 and a variance of 1 across all dimensions. But the lifting transformation, that's where the topology comes in.
They use a look-back window of a specific size, which they call H1, and they slide that window forward by a specific offset called H2.
So that sliding mechanism basically converts a single long stream of log returns into an overlapping sequence of smaller data blocks.
Yes, and they associate a discrete uniform distribution to each of those smaller blocks. So instead of tracking a single price moving up and down on a chart, your time series becomes a sequence of empirical probability measures.
You're taking snapshots.
Taking snapshots of the recent neighborhood of price action, yeah, and treating all the data points within that snapshot as a unified geometric organism.
So we are tracking the shape of the data cloud as it evolves over time.
Exactly.
Now, if we look at the one-dimensional baseline, which is a foundational method the authors build upon from 2024, they utilize the 1D Wasserstein K-means method. Why is the Wasserstein metric the right tool for comparing these moving data clouds?
Well, the Wasserstein metric essentially measures the effort required to reconfigure one mass distribution into another.
Like the Earth mover's distance.
Yes, the classic Earth mover's distance. If you have a pile of dirt shaped like one distribution and you want to reshape it to look exactly like a second distribution, the Wasserstein distance is the absolute minimum cost of moving that dirt.
Okay, and in one dimension, calculating this is incredibly computationally elegant, right?
Oh, it's beautiful. Because in one dimension, you don't need to run a massive linear programming optimization.
You just sort the data.
Sorting is the key. The optimal transport plan between two one-dimensional distributions is strictly monotonic. You sort the values of the first distribution, sort the values of the second, and you pair them up sequentially.
And since sorting algorithms scale linearly, the distance calculation is lightning fast.
Exactly. Plus, a K-means algorithm requires calculating a barycenter, the mean distribution that sits at the center of your cluster.
Right.
In 1D, finding the Wasserstein barycenter simply involves taking the mean or median of those ordered sequences.
Okay, but I do see a mechanical overlap issue here. Yeah, if we are sliding a window across a time series, a single raw data point, say, a specific Wednesday at 2 p.m., is going to be captured in multiple consecutive snapshots.
Right, because the windows overlap.
Exactly. It might sit at the end of the first window, in the middle of the second, and at the beginning of the third. When the algorithm finally clusters these windows, how does that single Wednesday get a final regime label?
Ah, okay. The authors implement a conservative majority voting mechanism to resolve that overlap.
Oh, majority rules.
Basically. If that Wednesday at 2 p.m. is grouped into regime A in the first two windows, but regime B in the third window, the algorithm assigns it the label of regime A. It simply counts the cluster assignments for each underlying data point and takes the majority.
What if there's a strict tie?
If a tie occurs, the algorithm falls back to the prevailing pre-existing regime. It essentially assumes the market state hasn't changed until there is overwhelming mathematical evidence that it has.
Which brings up a structural question about parameter tuning. If this entire process relies on sliding windows creating these empirical distributions, how sensitive is the algorithm to the interplay between the window size, H1, and the lifting size, H2, when data is scarce?
That's a great question. The authors rigorously tested hyperparameter sensitivity using synthetic one-dimensional data. And they found that in low data environments, varying the window size in the offset step impacts clustering accuracy significantly.
I would imagine so.
Yeah. A smaller window size often captures local structure better and yields higher accuracy. But, and this is a big but, it becomes highly sensitive to the sliding offset.
Meaning if your step size is too large?
If your step size is too large relative to a small window, you risk jumping over a regime transition entirely. You just completely miss the structural shift.
Wow. And because this is an unsupervised learning model, a practitioner out in the wild doesn't have a ground truth answer key to check their accuracy against. So how do you know if you've selected the right window size?
You have to rely on internal validation metrics. You're trying to identify high-quality clusterings without labels. The authors point to two specific metrics for this.
Okay, what are they?
First, the final value of the objective function, which measures how tightly packed the data is within each cluster.
Got it.
And second, the mean centroid distance, which measures how well separated the different regimes are from one another.
So by running multiple random initializations and optimizing for tight, widely separated clusters, you can confidently select the best hyperparameters.
Precisely, even without labeled data.
Okay, so this foundational 1D logic is fascinating, but it brings us to the massive computational roadblock that Luan and Hamp actually set out to solve.
The multidimensional problem.
Exactly. Everything we just discussed works beautifully for a single asset. But financial markets are inherently multidimensional. Analysts evaluate portfolios, global asset classes, risk factors simultaneously. When you apply this optimal transport math to multiple dimensions, the simplicity just vanishes.
It completely vanishes. The optimal transport calculation becomes an enormous bottleneck.
Right.
In 2, 3, or 50 dimensions, you no longer have the luxury of just sorting the arrays.
Right.
Calculating a true multidimensional Wasserstein barycenter requires highly expensive numerical optimization. Or you have to use these intricate inverse radon transforms.
Which sounds painful.
It is computationally brutal. If you attempt to run an iterative K-means algorithm, which forces you to recalculate that barycenter at every single step of the loop, your computational cost explodes beyond any practical utility.
Okay, here's where it gets really interesting. How do they bypass this multidimensional roadblock? Because they don't actually calculate the full multidimensional distance at all.
Nope, they don't.
They use an approximation called the sliced Wasserstein distance. Let's build a visual for the listener here. Imagine we are looking at a complex three-dimensional cloud of data points floating in a room.
Okay.
Measuring the exact volume and shape of that 3D cloud directly is mathematically exhausting.
Right. So instead of measuring the 3D cloud directly, you project that multidimensional data onto a one-dimensional vector. Think of that vector as a line sitting on a unit sphere surrounding the data.
So we are essentially shining a set number of flashlights from different angles on that sphere, pointing inward at the multidimensional cloud.
I love that analogy. Yeah.
We aren't measuring the cloud itself. We are looking at the one-dimensional shadows that the cloud casts on the wall behind it, and we just measure the Wasserstein distance between the shadows.
That geometric visualization captures the math perfectly. You project the d-dimensional empirical measures into 1D shadows. Once the data is in one dimension, you can use that lightning-fast sorting trick to compute the distance.
Wow.
You do this across a finite number of projection directions, the flashlights, let's call them L, and you approximate the full multidimensional distance as a sum of these one-dimensional distances.
Okay, I follow the distance calculation, but what about the barycenter, the center of the cluster? If we are projecting into 1D to measure the distance, don't we eventually have to reconstruct the 3D cloud to find the new center for the next iteration of the K-means loop?
You would think so, but no. Luan and Hamp introduce a highly elegant algorithmic bypass in their implementation, which is detailed in Algorithm 1.
Oh.
They never reconstruct the multidimensional barycenter. They maintain a fixed grid of projection directions throughout the entire algorithm.
Wait, really?
Yeah. The multidimensional data is projected into those fixed 1D directions exactly once at the very beginning of the process.
Right.
They sort the arrays exactly once. From that moment forward, the clustering algorithm runs entirely in the space of the 1D projected measures.
They never go backward. They just cluster the shadows.
Exactly.
That is a massive computational saving. But it raises an obvious empirical question, you know? Do these one-dimensional shadows actually preserve enough topological information to accurately capture complex multidimensional regimes?
To validate that, the authors generated some really robust synthetic datasets. They built 2D and 3D time series using geometric Brownian motion.
Okay, so simulating actual market behavior.
Right. They simulated 20 years of data, assuming 252 trading days a year, 7 hourly observations per day. And they explicitly engineered overlapping regimes with distinct annualized means and volatilities, effectively defining mathematical bullish and bearish states.
And since they engineered the data themselves, they knew exactly where the regime transitions occurred,
Giving them a perfect key to score the algorithm's performance. But they didn't stop there. They engineered specific edge cases to stress test the model.
Like what?
One crucial test evaluated the algorithm's ability to detect correlation shifts. They constructed 2 regimes where the marginal distributions of the individual assets were absolutely identical.
Okay, meaning if I only looked at asset A in a vacuum, its mean and volatility never changed across the entire 20-year simulation.
Right. And asset B also looked perfectly stable in isolation. The only variable that changed was their joint behavior.
Their correlation.
Exactly. In the first regime, the correlation between the 2 assets was positive 0.5. In the second regime, the correlation flipped to negative 0.5.
So a traditional one-dimensional regime classifier running on each asset independently would completely miss the transition.
Completely. Because the shift only exists in the multidimensional space.
And the sliced Wasserstein K-Means's algorithm caught the correlation flip.
It isolated the regimes perfectly. Even though the individual components appeared unchanged, the overall geometric shape of the joint distribution shifted when the correlation flipped.
Because the flashlights captured the change in the shadows.
Exactly. The algorithm successfully clustered the new regime.
Wait, before we declare this a revolution, I have to push back here.
Go for it.
As someone who has built market models, if I see a data set featuring overlapping regimes with distinct means, volatilities, and correlations, my immediate instinct is to pull a standard industry tool off the shelf.
Like a hidden Markov model.
Exactly. And HMM is quite literally designed to find hidden, latent states based on observable outputs. Why are we reinventing the wheel with optimal transport math when an HMM can map those correlation flips?
The paper actually addresses that exact comparison. A hidden Markov model performs exceptionally well on that dataset, assuming you feed it standardized returns. However, an HMM's accuracy relies on a critical underlying assumption.
The data has to be multivariate Gaussian.
Yes. It assumes the data forms neat, multidimensional bell curves.
And financial data is notoriously non-Gaussian. I mean, we deal with fat tails, skewness, volatility clustering, highly asymmetric dependencies.
Exactly. So to expose that vulnerability, Luan and Hamp subjected the models to a non-Gaussian stress test. They utilized the make-moons function from the Sklearn Python library.
Oh, to generate that moon-shaped data.
Right. They generated a regime where the joint distribution of the 2 assets physically resembles 2 interlocking crescent moons. This creates a nonlinear dependency structure that a standard covariance matrix simply cannot describe.
So if you force an HMM to look at non-Gaussian moon-shaped data, What happens to its hidden state predictions?
The parametric assumptions of the HMM cause it to fail completely. It attempts to stretch a rigid Gaussian ellipse over a crescent moon, and the resulting regime classifications become essentially random.
Wow.
The slice-Wasserstein approach, however, is entirely distribution agnostic. It does not care if the data cloud resembles a bell curve, a crescent moon, or a scattered ring. It only measures the realized geometry.
So it found the moons.
The Strzocki-AJ algorithm successfully isolated the moon-shaped regime with high accuracy, yes.
That perfectly illustrates the danger of relying on parametric models when the underlying topology gets weird. But, okay, the algorithm can find a crescent moon in a sterile laboratory setting.
Sure.
But actual trading floors aren't sterile. They are noisy and chaotic. How does this elegant math hold up when exposed to real-world macroeconomic shocks?
They tested that too. For their real-world crucible, the authors assembled a massive data set of over 100,000 two-dimensional data points. They analyzed the hourly spot rates for the U.S. dollar against the Japanese yen and the British pound against the U.S. dollar.
Over what time frame?
Covering April 2007 through August 2023.
Okay, so that 16-year window encompasses the global financial crisis, the European sovereign debt crisis, Brexit, and the onset of the COVID-19 pandemic.
A very turbulent window. And they applied the hyperparameters they validated earlier.
Oh.
A 60-hour look-back window, sliding forward in 12-hour increments using 16 fixed projection directions.
Okay.
But one parameter choice really stands out. They explicitly set the algorithm to search for 3 distinct clusters, k equals 3.
Interesting, because in traditional risk modeling, we often default to binary states, risk on or risk off. Why force the algorithm to find a third regime?
Setting the target to 3 clusters forced the algorithm to tease out nuanced joint behaviors beyond a simple high variance versus low variance split. It challenged the unsupervised model to identify intermediate states or perhaps fundamentally different types of market stress.
So what did the algorithm actually uncover across those 16 years of currency data?
It cleanly partitioned the timeline into 3 distinct market states. Regime vol and regime second represented relatively benign, typical market conditions. Both regimes exhibited negative correlations between the 2 currency pairs.
Okay, and the difference between 1 and 2?
Regime the second showed slightly higher variance and small negative returns compared to regime the first. So a mildly elevated risk environment, but structurally the 2 regimes behave similarly.
Then there is regime the third, the anomaly.
Regime the third defined a heavily stressed market state. It featured massive volatility spikes and large negative average returns across both currency pairs simultaneously.
Right.
The defining characteristic of regime the third, however, was the structural breakdown in dependencies.
The correlation flipped.
Yes, exactly. In the benign regimes, the correlation between USD-JPY and GBP-USD was predictably negative. In regime the third, that correlation violently flipped and became decidedly positive.
The fundamental relationship between the assets just reversed. And if you look at the historical timeline, the algorithm operating with 0 historical context, 0 economic inputs, no parametric assumptions, it activated regime the third during the exact periods of the 2008 global financial crisis and the March 2020 COVID-19 liquidity shock.
If we connect this to the bigger picture, during those specific windows, the global demand for U.S. dollar liquidity overpowered all other idiosyncratic currency drivers.
Right, because every asset was simultaneously being sold to raise dollars.
Exactly. The normal correlations broke down. And the algorithm detected that specific geometric distortion purely by clustering the evolving distributions.
That selectivity is incredible, because there were numerous other massive volatility events in that 16-year window. I mean, in 2016, the Brexit referendum caused the British pound to crater historically. In 2022, the Truss Kwarteng mini-budget caused a meltdown in the UK gilt market. But the algorithm largely ignored those events when assigning the stressed regime the third label.
Because the algorithm recognized that Brexit and the mini-budget were severe, but ultimately localized shocks. They fundamentally altered the trajectory of the British pound, but they did not cause a systemic, global liquidity squeeze that uniformly impacted the Japanese yen.
The joint distribution of the 2 pairs didn't exhibit that systemic positive correlation breakdown.
Exactly. The sliced Wasserstein method proved it could mathematically differentiate between a localized country-specific panic and a global systemic contagion.
Just by analyzing the shadows of the data.
Yeah.
I mean, for a quantitative strategist or a risk manager allocating capital across a global portfolio, having an automated, model-free tool that can distinguish between idiosyncratic noise and a true systemic correlation breakdown, that is invaluable.
It's a game changer.
But we do have to adjust the boundary conditions. Where does this methodology break down?
The primary limitation identified by Luan and Hamp is the classic curse of dimensionality. Remember the analogy of shining flashlights at the data cloud from a unit sphere?
Yeah.
The algorithm relies on a fixed grid of projection vectors scattered across that sphere. If you expand your analysis from a 2-asset currency pair to a 50-asset equity portfolio, the surface area of that multidimensional sphere grows exponentially.
Right. So to maintain the same density of flashlights, to ensure you aren't completely missing important topological features in that massive geometric space, the number of projections has to scale up too.
It has to scale with an exponent of the dimensions -1. The required number of projections quickly becomes staggering.
Wow.
While the sliced Wasserstein approximation is highly computationally efficient for 2-dimensional and 3-dimensional data as the dimensions grow large, maintaining an adequate grid of projection vectors makes the algorithm computationally intractable. It simply takes too long to run.
Did the authors suggest any architectural workarounds for analysts dealing with high-dimensional portfolios?
They do. They suggest utilizing Monte Carlo random sampling to dynamically generate the projection vectors rather than relying on a fixed uniform grid.
Okay, so randomizing the flashlights.
Yeah, random sampling can alleviate the exponential scaling issue, though it introduces stability trade-offs that, well, fall outside the immediate scope of this paper. They also point toward alternative non-parametric methods, such as utilizing rough path signatures.
Oh, I've seen that in the literature recently for clustering highly dimensional data streams.
Exactly. It shows a lot of promise.
So what does this all mean? Synthesizing the core contributions of Luan and Hamp for your own models, they have successfully bridged the gap between financial regime switching and the unsupervised clustering of optimal transport.
Yeah, that's the key takeaway.
By implementing the sliced Wasserstein approximation alongside their fixed projection algorithmic bypass, they provide a highly efficient, model-free framework to identify multidimensional market states.
You don't have to guess the correct underlying distribution. You don't have to rely on multivariate Gaussian assumptions. You just cluster the geometric projections of the raw overlapping data.
It frees quantitative analysts from the constraints of structural assumptions. It allows the data topology to speak for itself,
Revealing joint dependencies and correlation flips that traditional parametric methods frequently obscure.
I want to leave you with a final provocative thought regarding the application of this research, because everything Luan and Hamp analyzed in this paper relied on realized historical return distributions.
Right, looking backward.
But the mathematics of sliced Wasserstein K-means is fundamentally just clustering empirical measures. What happens if you apply this exact mathematical framework to forward-looking distributions?
Yeah, that points toward the derivative markets.
Exactly. Imagine applying this volatility surfaces of options arrays in real time.
Because an options chain is essentially a massive, evolving probability distribution of future market expectations.
Right. Could you use this non-parametric method to cluster implied regimes? Could a risk manager detect systemic correlation breakdowns and topological shifts in the options market before the underlying spot assets even begin to crash?
That is definitely the logical frontier of this methodology. If the algorithm can map the geometry of past systemic shocks without parametric bias, it absolutely possesses the mathematical capability to map the implied geometry of future systemic shocks.
The structural breaks and rigid mathematical models of traditional econometrics might be failing us when the markets get chaotic. But by embracing the complex topology of the raw data, by learning to measure the shadows on the wall, we might discover a new, deeply quantitative way to understand market regimes.